Okay, hi everybody. This is the first video for Science Chapter 9. So what I would like you to do right now is two things. I would like you to have your science textbook out, and it should be open to page 218. I would also like you to have your science activity manual out and open to page 146. So it's textbook 218, activity manual, page 146. And we're starting our next unit called sound. Now, I'm going to pull up the PowerPoint, like I usually do, to help us with these things. So, look at paragraph 1 in your textbook. Properties of sound waves. Engineers like Mr. Fogel must understand sound to design technology that can be used to help others. What do you know about sound? Sit quietly for a moment and listen. You may hear the hum of air moving through a vent, or the ticking of a clock. Perhaps a noisy truck or train is passing nearby. A chair may squeak, or shoes may rustle on the floor. Although each sound is different, all sounds are made in a similar way. Each sound started because an object moved. Sit still for a moment. Listen. Dog's paws hitting the kitchen floor and his chain jangling. Somebody in my kitchen is running water in the sink. So, the book just told us that every sound started because something moved. Okay, so looking at the next part of your book, it says vibrations and waves. So we start with the definition of a vibration. The movement of an object causes vibrations. A vibration is a rapid back and forth movement. So in your book, you're going to highlight that, okay? Just like we would at school. A vibration is a rapid back and forth movement. Demonstrate it with a rubber band. Not ideal, but you can kind of see it. So I hold the rubber band like this, and then I gently flick the rubber band. You can see the rapid back and forth movement, vibration. If you play a stringed instrument, I know some of you do, when you pluck the string, it vibrates, and that's what gives you the sound. The next sentence in the book gives us our basic definition of sound. Sound is a vibration that can be heard. So you're going to highlight that as well. The ticking that comes from a clock is caused by the movement of the parts inside the clock. The parts vibrate as they touch each other. They cause the air molecules around them to vibrate too. These vibrations blend together to make the ticking sound that you hear. Okay, so first we have vibrations, rapid back and forth movement. Vibrations are responsible for sound. Sound is vibrations that can be heard. Now, I have a video to show you. I'm only going to show you a small part of it, but it will help you because when we talk about sound, sound is invisible. So when we talk about things that are invisible, we have to use our imagination to picture a sound wave. This video, there's going to be a couple of experiments that will show you what sound waves do. Sound waves are invisible. You are never going to be able to look at them and see them. But this will show you that sound waves exist. And this is a show
curious?
from PBS.
Today on Curious Crew, we have some interesting investigations planned. Isn't that awesome? Whoa! No way. We'll check out some space phones. Go back and... Whoa, did you hear something cool? Make a cymatic demonstrator. Yes! Listen to some magic spoons and learn to play a straw. In other words, we're going to explore sound.
Production of Curious Crew is made possible in part by a grant from Michigan. Information is available at TechSmith for families to play, create, and challenge their understanding of science.
Hi, welcome to Curious Crew. I'm Rob Stevenson, and we're coming from Impression 5 Science Center. And we've got some unusual things today. But before we get started, I always like to start with a discrepant event because it stimulates curiosity. That's what I'm talking about. And I've got something really strange to show you. In fact, I've got here a big speaker. And what I'm going to do with this big speaker, I'm going to put a pan of water very delicately on top of this big speaker. And I've got this big speaker hooked up to my computer, and I'm going to play a tone from my computer. But watch the pan of water when I do this. Keep watching that pan. Now, I'll stop it for just a second. You started to see some crazy things going on in there, which was really, really neat. Makes us start to think and wonder, doesn't it? Anybody have a guess what today's subject might be about? Alex, what do you think?
Sound?
Sound is exactly right. Stick around and you'll understand how we did this unusual discrepant event, and we'll get to explore lots of things dealing with sound vibrations. So stick around. Vibrates back and forth.
So
begins to vibrate.
Sorry about that. So when he put the pan of water on top of the speaker and then he made sound with his computer, the sound waves, those vibrations, are what made the water jump and move. So even though you couldn't see the sound wave, you could see what the sound wave was doing. I'm sorry, I'll move back a little bit on the video and we'll go back to what he was saying next. Okay.
Try stretching out a rubber band and pluck it. You can see it wiggle and vibrate. That wiggle continues in the air in little waves that we can't see, but we can feel them and hear them. And when those waves get to our ears, our brains interpret the sound. Whenever you're exploring sound, the first tool you have to get is one of these. What's this, you guys? A tuning fork is exactly right. The neat thing about a tuning fork is when you strike it against something rubber, well, it doesn't seem to really do anything, does it? But if we strike it against the rubber and then place it on the table, it actually resonates the vibration through the table and you can hear it as sound. Now, strangely enough, when we strike this, it's moving so fast. This one 320 times in 1 second, back and forth. Well, we can't see that, can we? No.
Wow.
But we can show it. Would you do me a favor? You hold it by the base there, and I'm going to ask my friend, yep, go ahead, Ryan.
Right,
You're
we're
going to strike that.
see
and I'd like
what
you to
the
put it in
sound
the
wave
water.
does.
Isn't that awesome? Do it one more time. Amazingly, we see a vibration, a little splash in the water itself, because the vibration, the movement coming off of the tines of the fork moves the water.
You can see
Let's
what
try
the
something
sound
else.
wave
John's
does.
going to hold up this little ping pong ball that I have on a string, and we're going to try to get it nice and steady. And I'm going to come in with the tuning fork and notice that energy from the tuning fork pushes that ball away. Amazing. Let's show it one more time, this time with paper, okay?
This one's cool.
Strike the tuning fork. I'm going to hold it up to paper. What do you think is going to happen?
It's gonna
Oh, I love
make
it.
noise.
Buzz makes the
It's
noise.
gonna make noise on
Okay,
the paper.
I love it. Let's see. That was an excellent prediction, you guys. 320 times a second, those tines are moving back and forth. We can hear the energy on the paper, even though our eyes can't see it very well. Do me a favor. Zach, would you pluck this rubber band? I've got a rubber band stretched between a couple of nails here, and you'll notice when we strike it, it wiggles. It's a vibration, and in fact, sound is nothing more than vibrations. Vibrations that move through solids, liquids, and gases. Now I'm going to do something else and real lightly, hold up 1 second, Zach. I'm going to put a couple pieces of paper strips on the rubber band, and now gently pluck it. You'll see the energy transfer, whoa, right into those paper strips. See if you can bounce that one off. Pretty amazing. Now, let's imagine for just a second that we're a solid table like this, right? It's really massive, the molecules are squished together, and believe it or not, sound can travel through solids, they can travel through liquids, and they can travel through gases. Here's the most amazing thing. Do you know that sound travels better through solids than through the air? It's true. Fascinating. Science is amazing, isn't it?
Yeah!
Good job, you guys. I know, it really is. When we speak, our vocal folds in our throats use exhaling air to make them vibrate. They wiggle very fast, from 100 to 1,000 times every second, which we can hear as sound. Place your hand gently on your throat and hum. Can you feel the vibration? Remember, vibrations make sound.
Okay, so I wanted to show you that because I feel like it was a really good way to see the effect of sound waves. Like I said, sound waves are invisible. You're not going to be able to see them, but you can see the effects of them. We saw how the sound wave made the rubber band vibrate and the paper flew off. A really cool experiment with the tuning fork. When it touched the paper, you could hear that buzzing sound. So sound waves, sound is vibration that can be heard, and sound travels in sound waves. Before we go on, we're going to look at this little section that says fantastic facts. You may have heard the shrill trumpet sound that an elephant makes, but a deep growling or rumbling noise is a more common way that one elephant communicates with another. Infrasound is a sound below the level of human hearing. Many of an elephant's rumblings use infrasound. The vibrations of an elephant's infrasonic messages and warnings can be heard by family members miles away. Both humans and elephants make sounds as air causes their vocal folds to vibrate. Just like we just saw in the video, you have vocal cords. And like he just said in the video, if you put your fingers right on your throat and talk, you will be able to feel the vibrations that your vocal cords are making. Remember, sound is vibration that can be heard. Vocal folds are strips of tissue that lie across their airways. An elephant's rumbling sounds are made as puffs of air cause its vocal folds to vibrate. The vocal folds of an elephant are about 8 times larger than those of a human. Its very large folds vibrate much the way a flag flaps in the wind, resulting in the low infrasound. So we're going to learn a little bit later in the chapter that there are some sounds that are so low that the human ear cannot hear them. And this example from Fantastic Facts is the sound that elephants make. Their sound is so low that the human ear cannot pick it up, but the elephants can. And this is one way that they communicate with each other from miles away. All right, now we're going to look at the bottom of page 218 for our next definition. And you can also look at the screen. Sound moves through matter in waves. A wave is a disturbance that moves energy from place to place. So you're going to highlight that in your book. And you can look at the picture on the screen as well. So down here at the bottom, you see an example of what a sound wave looks like. Now, it might remind you of a slinky, which is what we would use to demonstrate what a sound wave actually looks like. Unfortunately, my slinky is at school in the closet, so I don't have it here. But I did find a video of kids using a slinky to show what the sound wave looks like. So it's really short. I'm just going to show you. This is what I would have shown you if we were at school. Watch the motion of the slinky.
Compressions in the slinky are when the molecules are spread apart, which is when the slinky looks like it is moving. Rarefactions are where the red part is on the slinky. The red part is on the slinky.
Okay, so that was just a little demo. If we were in school, I would have had two of you hold the slinky and we would have demonstrated that. So the movement of a slinky, when you put pressure on one end of it, is the same movement that a sound wave goes through. So if you look at the top of page 219, we'll start reading there. It says, the matter through which a sound wave travels may be a solid, a liquid, or a gas. Most of the sounds that we hear travel through the air. So most sound waves travel through gas, through the air. But sound waves can also travel through liquids. If you've ever been underwater in a swimming pool and someone makes a noise nearby, you can hear it. Sound waves also travel through solids. If a fire engine or a police car goes by outside, a really loud siren, those sound waves travel right through the wall of your house and they reach your ears. Sound can travel through solids, liquids, and gases. Next paragraph says, sound energy moves from the vibrating object to the ear. You hear sounds because the vibrations of sound energy cause your eardrum to vibrate. As the vibrations are carried through the bones of your middle ear, the vibrations are changed into nerve messages. Your brain then interprets these messages and tells you what you hear. Sound waves are also described as mechanical waves. Mechanical waves must have matter to travel through. I would like you to highlight that sentence because it's really important. Mechanical waves must have matter to travel through. And sound is a mechanical wave. It cannot travel if there is no matter for it to travel through. Energy causes particles in the matter to move and vibrate. Sometimes you can feel sound waves. When you hum, for example, you can feel the vibrations that your throat makes. Those vibrations cause the sound that you hear. Other sounds that you might feel are loud thunder or the beats of a bass drum. Now we're going to talk about how a sound wave moves. I'm going to show you a picture first. So remember we said that the slinky demonstrates the motion. So as the sound moves, when the particles are close together, it is called a compression. When the particles are farther apart, we call it a rarefaction. Okay? So compression's pretty easy to remember because we've learned the word compress. It means pushing something closer together. So when the particles are close together, the compression, far apart, rarefaction. Look at the top of the second column of page 219. In a sound wave, the particles of matter vibrate back and forth in the same direction that the sound energy is moving. The motion of each vibration pushes together some of the particles of matter. This part of the wave is called a compression. Okay? Highlight that in your book as well. As the motion of the vibration moves away from the compression, the particles spread apart again. This part of the wave is called a rarefaction. Here. Waves continue to form as long as the object vibrates. The way sound waves move is similar to the way a spring toy or slinky moves. If you stretch out a spring toy and push one end, the coils of the spring move back and forth as the wave passes to the end of the spring. The particles of matter are not carried along with the sound wave. Each particle vibrates but remains in its place. Imagine what would happen if air particles were carried with the sound wave. Sound waves from a choir singing would cause a wind to blow. Okay, so at the top of this page, too, they have a picture that shows you what a rarefaction and a compression looks like, and I will attach this PowerPoint to the lesson, so you will also have this picture to help you remember the difference between a compression and a rarefaction. Now, I also ask you to have your science activity manual out to page 146. So your page 146 is going to be kind of like a graphic organizer with all of the information that we learned about today put into it. Now, I did not have a copy of this that I could use on the computer. So what I did was I put each definition on the PowerPoint for you. So you're first going to look at the box that says vibration. It is orange. Underneath of vibration, you are going to write the definition. Here it is on the screen. Rapid back and forth movement. Rapid back and forth movement. Vibration. Okay, so write that in the orange box. Give you a moment to do that. Okay, the next one you're going to write the definition of is a wave, a disturbance that moves energy from place to place. Disturbance that moves energy from place to place. Wave on page 146 is also an orange box. So go ahead and write that definition in. Okay, the next thing you're going to do is fill in the definition of a compression. It is underneath of a wave. It's broken into two boxes, compression, rarefaction. The compression is when vibration pushes together some particles of matter. When the part of the slinky, which is our demonstration, when they're close together, that's a compression. Go ahead and write that in the purple box for compression. Okay, and the last one we're going to take a note for today is rarefaction. When the vibration moves away from the compression and starts to spread apart. We saw in our demonstration and in our pictures. Rarefaction. When the vibration moves away from the compression and spreads apart. And don't forget, I will be including this PowerPoint for you. And you have a picture of this at the top of page 219 to remind you as well. So this video covered pages 218 and 219. As a little recap, a little review, we first talked about the fact that vibration is a rapid back and forth movement, and that sound is vibration that you can hear. Sound waves can travel through solids, liquids, and gases. You hear the sound because the sound waves enters your ear, vibrates the parts of the middle ear, and then your brain interprets that and tells you what you are hearing, and all of this happens almost instantly. We also talked about the fact that a wave is a disturbance that moves energy from place to place, and we talked about the fact that sound waves are mechanical waves. A mechanical wave must have matter for the wave to travel through. If there's no matter, the mechanical wave cannot travel. And last but not least, the two parts of the sound wave. Compression, close together, rarefaction, further apart. Okay, that is our first lesson, and I will see you next time.